today we're going to talk about orders of differential equations. Or actually, that'll be our first part because we didn't talk about this last time here. We did a few examples, and those examples encompassed what we call being different orders of derivatives or differential equations. And the reason that it's important in a sense is because sometimes you are asked questions about taking something to X order, whatever it might be, and it's good to know what it is. So this is just a little bit of a conceptual thing. So a first order differential equation involves a first order derivative in it. So let's just put up here two examples, and in fact I am going to use the one that we did in example 1 in our last class, which was y prime plus 2, I believe it was 2y. Yes, 2y equals 0. In fact, I should make this y a regular y, so you don't think it's special in any sense. So here's a first order differential equation. As you see, we have a first derivative, hence the name. So if you're ever asked to take something to a first order derivative, you know that somewhere in your answer you'll have whatever your variable is, whatever you're using for that function, to the prime notation, so the first derivative. Now, being that I think it's very easy to identify a first order derivative and a second order, does someone want to give me their own example of what a first order derivative might be?
Y prime
Alright, so always a good place to start.
plus 8y equals 0.
8y equals 0. That's another good one. The key part in any order of a derivative is that, or in this case, of a differential equation, of your derivative needs to be to whatever power that order is. So if it's first order, we'll have a first derivative in there. For second order derivatives, I'm going to use the other example that we did in class last time, which was our second order differential equation. I keep just saying derivative. I should be saying differential equation. So here we have our second derivative of y plus 9y equals t. And these should look familiar to you because we did, in fact, do example 1 for first order differential equations and example 1 for second order differential equations in our last class. Who wants to give me an example of the second order differential equation for our second example in our outline here on the board? It's very challenging to be wrong.
Y, second derivative, plus,
So y double prime,
plus 27y equals t.
27y, you want to put a y there?
No,
Can you
That's what,
use,
you can, you don't have to.
can you use like
Well, that's what I'm
minus
putting.
signs?
Oh, yeah, yeah.
That was all.
it could be any
You want to
number.
make it a minus this time? Yeah. Let's mix it up so that we know that it can be a bunch of different things.
And you don't need the y?
You don't need to have another y value as
Nope.
long as you have a y.
We'll take that out too.
So as long as you have a y double prime, you can, if it's,
So what do we want to make it equal to?
R.
does it have
R?
to equal 0?
Nope, it does not. See here in our second order we had equals t, here we have equals r, another variable.
So it can equal anything.
Again, the key for a second order is just seeing that we have a second derivative of a function somewhere in there. And we're happy. Quick review. First order differential equations will have a first derivative. Second order differential equations will have a second derivative inside. Does anybody require more time? We're good? So now solving differential equations. Last time we looked for solutions. How did we find solutions last time? Did we do?
Last time.
Yeah.
Let's go.
What did it mean to find a solution?
Do you take the anti-derivative?
You know, seeing if something works.
That was it, yeah. We would have some differential equation, and then we would be given, say, another function, and we would have to match that function up to the correct derivative in our differential equation. So if we were given something like example 1 here for our first order differential equation, and we had some function that we were going to check and see if it was a solution, we would at one point have to take the first derivative and plug that in for y prime, and we would leave it alone and just plug it in for y here. And if in fact that did equal 0, once we did that, it was a solution. So we looked for solutions there. Now what we haven't done was attempt to solve them in any way. Now, for our calculus folks in here, I'm sure we've talked about
Yeah.
anti-differentiation at this point now.
Yeah.
What is
The
anti-differentiation?
opposite of the derivative. It's like going backwards from the derivative.
It's going back. Have you talked at all about integration and integral?
Yeah.
Yes.
Sometimes it's known as the antiderivative, right?
Yep.
And for those of you not in calculus, it's actually a very simple procedure in the sense that whatever you do to get the derivative, say you're using the power rule, you just do it backward. So in our power rule example, we would move that power of our exponent out in front and multiply the equation by that, and then subtract 1 from our exponent. When we're doing an antiderivative, or doing an integral, what you'll do is you'll first add 1 to the exponent there, and then
Divide.
rather than multiply, you'll divide by it. Would you like me to do a really quick? Okay. All right. Let's just put it right here. So if we have, say, x squared f of x equals x squared, the first derivative would be
X.
2x.
X.
2x.
Oh, first derivative.
Right. So now let's say we are given f prime of x equals, let's say, 3x. And we want to know what f of x is.
3x to the third over 3, so the 3's cancel out.
Let's think about this here for a second.
Over 2.
Okay, so remember I said first we add 1 to the exponent. So if we have, this is an invisible 1 here, so if we add 1, it becomes x squared, right? And then we divide by the new exponent. There we go, so it's 3 halves x squared.
Do we have to put plus c?
Yeah, usually you, yeah.
'Cause it's
yeah,
not
you
a
would,
definite?
Because c could be any constant, it could be 0, in which case this is your total answer. You might have a 7 that's here, because when you take the derivative of something that doesn't have the variable x in it, in this case, it just disappears. But we'll keep
We don't have to add c for this.
What's that?
We don't have to then. I mean, because in calc we like add it whenever it's not a definite one, but we don't
In
add
an
it.
indefinite.
But when it's definite, we don't add it.
when it's definite, you have some sort of boundary that you're looking at, and then you're fine with that. So that's what the anti did, just backward. And you can see here, if you took the derivative of this, so you bring 2 down out front, the 2's would cancel here, subtract 1, you would get 3x. It's just backward. There's nothing much. Let me get my first example here. Alright, so let's take a differential equation that is y prime equals 3t squared minus 4. So if we were to find the value just for y, so we have y prime, what would y be?
3.
T to the third minus 4t.
T to the third minus 4t, right? I'm going to make a little bit more space here for myself. So that y is t to the third minus 4t. And we will throw in a c here.
So you just added 1 to the exponent,
Then divided by.
then divided by 3.
So that's why the 3 is canceled. 3
Okay.
divided by 3 is 1, and we have 1
Here.
here. And here this would have been
4,
t to the first, or t to the 0, I'm sorry.
and you add 1, so it's 2 to the third.
And then divide by 1, the number stays the same. Right. Now, very quickly, why do I add the c here? This is a good conceptual thing.
Con, if it,
Constant.
Just whenever you have
Whenever you have a number.
just a constant hanging out, it goes away. You don't
Right,
know
right.
if you had a constant or not, so.
From this original one, you don't know if this was maybe plus 7, plus 10, plus negative 30. Either way, the derivative of that, since it does not have a t in it, will just become 0 anyway. But you don't know if it's there. You don't know if it's there. How about we just do one example there for the sake of time, because that's fine. Let's look at a graph for this one here. So I've set up our axis here for y and t, and in this case, 1, 2, 3, 4, 5. And I'll explain after I put them up here, so just bear with me for a minute. I'll draw on that arrow, just so we aren't confused. This is what the graph is for example 1, I already wrote it down. Let's be as clear as we can be. Now the reason that we have these different ones that it could be is why. I'll ask one of you, what do you think? What do you think these different versions here represent? What's the one uncertain term here you have in y equals, what's that?
C.
C value, right. So this would be a case here where c is equal to 5. Right here, this would be a case where we have c is equal to 0. It just tells you where it's intersecting with your y-axis. If you need to bump it up more down below, this would be c value for -1.
So,
You're just not
when
certain.
you graph that, how did you know where to like cross the axis, the y-axis?
Well, that's a good question, because I've heard that graphing sometimes can be a bit of a struggle, because I've consulted with your calculus teacher, and sometimes graphing functions can be tough. A little technique that I personally used, I would, if I wasn't familiar with this shape, anytime you have a cube, you're going to have this shape here that we've produced, but if you're not certain, you might want to pick like a zero value, so see what it would look like, what you get if you plug in 0 for p, where you end up with there. Then pick like a couple positive numbers, a couple negative ones, just enough so you can start to build a picture. And if you do that, that's what you produce.
But, I mean the C, like, because the C is like the y-intercept, right?
Sure, so let's,
So like,
Let's-
if you just decide, I want C to be 5, I want C to be 0, and that's how you just drew it.
you got it.
Okay.
Technically, I could have an infinite
You can
number,
have like, yeah,
an infinite number of graphs here, yeah.
okay.
Because I could pick 5.0001, and that would be tucked right there. It would be
So
slightly
an
different.
artistic decision. Just
Yeah, just some examples.
Okay,
Yeah.
cool, thanks.
Very good, very good. All right, let's see. Okay, all right. So, we're moving on here now to equations that give properties rather than necessary full solutions that we would want. If we had an equation that might be y prime is equal to 2y. This equation doesn't give a specific solution to y prime, rather it gives a property of this differential equation. What it's saying is that y prime is proportional to y, and this will be key for our example on Newton's law of cooling here in a minute, by this coefficient of 2. So essentially, y prime is the same thing as our function y, as long as you multiply it by 2. So we have that property. Now, B up here in our outline is hitting at a key point in that, as of right now, for the tools that we have, there's only one way that we can solve this, and that's to know in advance what the solutions look like. So 4y prime equals 2y, and I wouldn't expect you to know this. Y would be some constant, say the constant of proportionality, e to the 2t power. So that e is our exponential, you know, it has a value. I think it's most helpful if you think of it as an exponential in that form rather than thinking of the value itself.
Forgot what's E in like real, it's in minus.
I believe it's something like 2.7 something.
2.7.
Is that right?
2.7.
Yeah.
2.7.
No, it's 8, 2.8.
It's like 3.
It's somewhere around 2.7. Long story short.
So C, E to the 2.
Yes, yeah. Now, if you want to be specific in how you would, so like if you want step by step, you would take the integral of both sides, because the antiderivative is integrating. That'll give you the original function. So if you integrate a derivative, you'll get the original function, because it's like saying we went forward into the derivative, now we're going back, so what would that give us? It would give us the original function. And when we do it on this side, we have here y, which doesn't have a power or anything like that. And just take my word for it right now, because solving this in a long way takes some time.
So we're trusting.
But this is, you're trusting me, yeah.
Okay.
This is the form. And believe it or not, I come across this practically every day in physics. And it's just easier if you know that if you're solving a differential equation in this way, that's a solution. That's what it looks like. graphs here of this fun. Up here, this would be, we're given C equals 5, this looks like C equals 2, so C equals -1. So a couple things here. We should point out the difference between a solution to a differential equation versus an algebraic equation. And that's that an algebraic equation typically has, in your low level algebra and whatnot, when you're solving an equation, you get one value, right? Well, when you're solving a differential equation, you're getting a function. And because it's a function, technically you could have an infinite number of solutions. That's the difference. When you solve for a function, you can have anything that you might plug in to be a part of that function. And you know that numbers are infinite. You can have an infinite number of solutions. That correspond, like in this example, to a specific shape, but you can have an infinite number of them. Any questions that we might have right now? All right, let's do an example. Then we'll take our break, and we'll be done for today. Like I said earlier, this problem is Newton's law of cooling. So here it is. And this is a little bit long, but bear with me. Suppose that a red hot steel rod, Romans and chocolate, is plunged into a bath of cool water. Let f of t be the temperature of the rod at time t. Suppose that the water is maintained at 10 degrees centigrade, according to Newton's law of cooling rate of change, and I'm going to underline this, and you'll see why in a minute, or rather it will become apparent in a minute, of f of t is proportional. And I'm going to underline this word as well. To the difference between the two temperatures. I'll note that they are 10 degrees Celsius and F of T. The rod and the water. Find the differential equation that describes this law. A nice place to start would be with the words I have underlined. Now, based upon what you know of differential calculus and proportions that we talked about today, how do you think we should attack this? Bless you. What is a rate of change? If we have a position function, so we're talking about the position of a soccer ball out there, and I want to know velocity, what is that velocity? What rate of change?
How it changes.
It's rate of change, right. So the velocity is a rate of change in this example that I'm giving to you right now.
With respect to time.
So it's the what?
It's with respect to time.
It's the derivative, right, of the position, right. Yeah. So if we are writing an equation that involves rate of change of f of t, then we should start by saying that f prime of t, because we're looking for rate of change as our derivative, and this would represent the rate of cooling since that's what we're looking for, because we're writing a differential equation that describes this relationship between the rate of change of the temperature of the rod as you plunge it into the cool bath water and the constant 10 degrees Celsius bath water that's there. So the rate of change of the rod, the derivative of that function, is equal to, now we just talked about constants of proportionality, and where did they go? Did they go out front?
They go in front.
Yeah, right. We'll assign this constant as k, so that's our constant of proportionality. Now what are we comparing?
The two
The
temperatures.
two temperatures, right. So 10 minus f of t. So in other words, there's some relationship between the rate of change of the steel rod that's proportional to this constant of the difference between the temperature of the rod and the constantly maintained bath water. Now this proportional term, from what we, ignoring the problem here, because we're going to use it in a second, can we be sure if this is positive, negative, or zero?
Okay.
We can't. Yeah. We'd have to know something physical about this example in order to be sure. And that's where our analysis of the problem here comes in. So in other words, can we use the problem to figure this out? And the answer is yes, we can. We you have your information. So, in the present, right when we start, so we have this red hot steel rod that I couldn't actually grab like this unless I had a robot hand or something. You need a grabber, but I'm going to plunge it into the water. What's going to be hotter, the rod or the water?
The rod.
The rod, right? Okay, so if f of t here is bigger than 10,
It's gonna be,
what's my rate of change here going to be?
negative.
Right, so, in other words, our rate of change describes the slope, so if we were plotting this
It would
in a
be
graph, we would see that the temperature of the rod would start to go down, so you'd have that negative slope. If we remember from algebra what a negative slope looks like. As I hold that rod in there over a period of time, what's going to happen to its temperature?
It's gonna cool down.
It's going to cool down, right? That graph, if we were to draw it, would be decreasing with time. So that means this term right here, f of t, since this is our temperature of our rod is a function of time, so however long we leave it in there, this will become smaller. It'll become smaller. Alright, so in that case, as we said in the beginning here, f prime of t would be negative, but it's good to note that this would shrink as well. And that's where that constant part comes in, because we always need some certain thing to relate it to. Alright, so if we need f, well, let's see here. Yeah, okay, so if we need this to be negative, we need the rate of change to be negative because it's cooling down with time. And we know that just this term in here from the start is going to be largely negative, and it's still going to be negative even as time passes, but the difference between the two will get smaller and smaller. What does k have to be? Positive?
Positive. Positive.
Positive, right, yeah. Because if it was a negative and this was a negative, our rate of change would be positive, which would mean that the rod is somehow heating up. That doesn't match anything. That wouldn't work. So, our differential equation, therefore, will be y prime equals k times the quantity 10 minus y. And we'll note that k is positive. There we go. That's not too bad. This requires some raw math here at first. And then we can better describe it just by looking at the physics.